So in case for the people who the BCI calculation did not work for, try it along with Guillaume, and if it's still not working, then we'll try to troubleshoot that a little bit.
Right.
Yeah.
How can I share my screen?
Just start share, I guess.
Oh yeah, I can just do that.
Yeah.
Just so give me 2 seconds.
So in the meantime, you can ask questions regarding like, was hypothesis testing, at least the steps that you go through, and how, what exactly you're.
Hello. Okay. There are layers. Let's make sure I have the actual, the right data.
Yeah.
Okay. Okay, I'll just share my screen now. I will share R. Just my screen. Okay. So, so here. So this is the code that we're gonna have for the second session. Session 2. Okay. All right, so I'm just really gonna reload the UNSAT data set. So I have it here in my environment. Still 110 observations at this point. Okay, I'm not gonna bother inspecting it at this point. I will convert the location and sex to factors because we remember it was a bit nicer to have it like that. I'll just inspect the data just to be sure that I have what I want. And remember, so that first variable X, we don't care. Location, we do, I guess, is 2 locations, 41 from Altai, 69 from Vacan. Sex is there's 57 females and 53 males. And we have the length, minimum and maximum, and all the summary for this. Something I forgot to do last time, we're going to use weight this time. But we didn't work on weight last time, so I forgot to do that step. And if you see, we have one NA value here, which we will remove because we don't want to have, if we want to calculate body condition, of course, we cannot do that without weight. So to be sure, we will remove that data for the calculation beforehand. If you didn't do that step, it's okay, because R would have done that automatically. When trying to calculate it, it would have known that it would have put an NA instead. So if you look at your BCI actually, and you try to do that with that NA without having removed it, you should see that one BCI value should be an NA as well, because R would not have managed to do that. Okay, I'm just going to plot again. So this is the plot that we had, and remember we remove the outliers, the fat dwarfs. Okay. So using the subset function. Okay. If we plot it again, so remember I can go on that line or highlight that line, and if I plot it again, which again tells you that having a script is handy, you can just go back to and rerun things after changing things around. Now you see that there is no outliers anymore, just that big one. Okay, now we're going to calculate the BCI. And we'll call this we'll call it method 1 for BCI. This will be body mass divided by body weight. Okay. Ideally, of course, what you want to end up with the body condition index is that leopards that are bigger but not very heavy for their size, you want the BCI to then be quite low, compared to kind of leopards that are more chunky, right? So leopards that are pretty heavy for their size would have a higher BCI. That's the notion. Okay, so like some people already demonstrate, like put in the chat, we're just gonna, let's just make a column that we'll call BCI1. I'll just put an underscore. BCI1, we're gonna assign the calculation here. So we said it would be UNCIA $weight divided by UNCIA $length, right? And that's it. Okay, cool. Okay, now let's do the second method. So if you, whatever, I think you can see my screen, right? Yeah, the second method I wanted to apply was that one. I'm not going to apply more. I'll just try two different ones and see what happens. The other one is the same as the last one. It's just that you log transform the variables beforehand. So you put log, it's log of body mass divided by the log of body length. So for this, I'm going to actually first log transform. Log transform weight and length. So I'm going to create a new variable actually. I'm going to call them, so the first one will be weight log, okay, log of weight. And it will simply be the log of UNCIA weight. Does that make sense? If I run just that, just to check what happens, I get the values here. Okay, you see I get an NA. That's the one that was missing. Which reminds me, I did want to remove it beforehand. Remove NA. So this is how NA. So this is how I'm going to do this. There's only a single weight value that has NA. So I'm just going to update UNCIA simply. So UNCIA will become something else. It will become UNCIA. So I will take UNCIA and I will just subset from it with the square brackets again. So the row, so that will be, there's a comma. Here will go the row index, and this is for the column. I want all the columns, of course. So I will not put anything here so that all the columns are kept. But here I want some kind of rule. I want to remove NA. And there is one way to do that is with complete cases. I'll just show you. I'll show you first what complete cases does on a different line. So if I type complete cases of UNCIA weight, this is what I get. I get a vector of, it's a logical vector. And I get true and false, right? Most of them are true. It means it's a complete case. There's no NAs. And there is one false. It's not the false being, it's an NA. It's not a complete case, okay? If I just copy this into the row index, it will return all of these apart from the row that is false. So it will not give me the 46 row. You can see this index 46. The false value is on the row number 46. Okay, so I'll just copy that, well, cut it and paste it here in the row index, and that will get rid of the NA. So I have 104 rows right now. If I run this, I should have 103, which is what I get. If I look at the summary now of UNCIA, you'll see that none of the columns have weight. Okay. So this complicates it. It's on weight because weight is the column that had an NA, right? Okay, now I'm gonna reapply the BCI. It will not change though, but I'm gonna rerun this. Now I'm gonna log transform the weight and create a new column in the dataset called weight log. Again, if I run all this now, okay, I can see there's no NA because I removed the NA before doing the log. So if I run these two lines, well, this line, I will end up with an extra column, and I want to do the same for length. So I'm going to call it length log, and it's going to be the log of length. Boom. I can plot log weight versus log length, and you'll see what happens. Actually, it's interesting. So plot x will be, yeah, this time not length centimeters, but it will be log length, the length log. And the y in my graph, so the y-axis will be unsia, log of weight. Okay, so it will be the same, the graph that I have here on the right hand side. It will be exactly that, but with the log versions of these variables instead. Cool, so let's do that. And this is why if I go, I can also go back to the graph I had before with the arrow here, and you'll see it's a bit different. Okay. What you actually, the thing is the length and weight, the way length and weight are related to one another is not a one-on-one relationship. Actually, you can't really see that here because we don't have a massive spread in the data, but this is a bit curved actually. So the longer you get, for every centimeter you get extra weight, right? But it's not, you won't get like, it's not you will get 1 unit of length and 1 unit of weight equally. The bigger you are, so if you get 1 centimeter, you'll get quite a lot of more weight. Sorry, it's a terrible explanation, but just to say it's not a one-on-one relationship. Having the log though, it kind of makes that relationship a linear, like a one-on-one relationship. At least something that is going to be a linear relationship, let's say. So let's just go back to that. So that's the log versus the other log. Now let's calculate the, so method 2 for BCI. It will be log of weight divided by log of length. Oops. So let's do it. Unsia, we call that BCI2. So we make a new column called BCI2, which will become, what did I say? Unsia weight, log of weight divided by unsia log of length. And why do I have an error? Something unexpected. End of document. Sorry, that's just my computer. Okay, so I'm going to run this. Just to remind you, to run something from the script, you highlight and you do Control Enter. I hope that was clear. Otherwise, you can also highlight and do run, or go on that line and do run. That will also
go on that line and Control Enter.
Yeah, I always use Control Enter. I think it's Control Enter. Okay. Okay, let's have a look. Just like let's take a look at what they are. Let's take a look specifically at these two variables. So I'm going to call unsia, but in brackets, I'm going to subset the columns. So I want all the rows, but I only want the columns BCI1 and BCI2. Okay, so I'm creating, this is a vector. It just means, okay, I want a vector with the names BCI1 and BCI2. If I put that in the column index, R will know that I want these column names. Square brackets, I close it, and then I close the round bracket to get the summary of these variables. If I didn't put, yeah, if I only run this without the summary, it will just return the entire columns like that. But with the entire thing, then I get a summary, which is kind of nice. So we can see,
also,
okay, there's
another way of doing the same, like subsetting the two columns could be if you do names unsia, it will give you all the column names for the data set and the positions. So instead of BCI1, BCI2, you could also just tell it the column numbers that you want.
Yeah, I can even look here, like in my environment, I have Uncia. I can unfold this and count, okay, 1, 2, 3, 4, 5, 6. That's BCI1 is column number 6. And the other one is column number 9.
Number 9, yeah.
So I could have done this as well. Instead of C, with the names of the column in between, I could have instead 1, sorry, what is it?
6, 9.
And 9, yeah. And that will be exactly the same thing. So this is like, R is kind of flexible in that way. That's kind of nice. You can refer to the data frames, you can refer to the column names, the column number, you can use the $ instead for a single column. I think there's other ways of, there's even more ways. All right. Okay, so what do we get? We get, yeah, we get an idea of how spread these BCIs are. Okay, but we don't, we're just gonna pick one of them. I'm gonna choose for the rest of the analysis, which will to apply the t-test. I'm gonna use BCI2. Yes, BCI2. And let's see what happens. Okay, so I'm gonna plot BCI2. I'm gonna create box plots. Maybe you've heard of box plots before. They are very nice ways of like, so we have, of course, we want to compare 2 locations. That's gonna be the main goal here of this testing. It's like we want to compare leopards from Altai with leopards from Wakan. Okay, that's just what we're going for. So of course, location is a categorical variable. So we're not gonna compare one continuous variable BCI against another one, right? It's not what we're doing here. Here we want to compare, we want to say that there's a categorical variable, which is the location, and we have a continuous variable. A very good way to kind of look at that data is with a box plot. And you want to say something, right?
I was saying we just split it and check the variation and distribution first to make sure that assumptions of t-test are met.
Yeah, okay, that makes sense. So that's true, yes, we have to check assumption, but first we'll look at the box plots and then inspect the data. Okay. Box plots for BCI2 by location. Okay, so there's a function called box plot. If I want to remind myself how to use it, I can put the question mark, remember? You can put just like this, or you can put the brackets also with nothing in between. To get the help file. Okay, so a box plot, okay. It needs at least an X argument, and then you can pass all the arguments if you want. By default, okay, if you put X, X needs to be some kind of number vector, right? So we can build a box plot for that vector. I can also use a formula. I will show you how to do that. So if I want to actually kind of subdivide the box, have several box plots for maybe for each location, for example, which is what I want here, then I might want to use the formula. I'll show you how to use that. Then there's lots of things you can pass on to that function. These are all kinds of arguments you can have. This is just for having like an X label, like a label for the Y-axis. So there's a lot of these are for simply the graphical, like just what you'll see on the plot. So don't worry about it too much. What's most important is the vector itself. Okay, let's try it. So let's just do a box plot first for Wakan. So actually what I'm going to do first is this. I'm going to create a vector called that I will call Wakan. Wakan BCI Wakan, maybe. Let's call it BCI Wakan. It's going to be an object, a vector, and it's going to be uncia $, and I said I would use BCI2, right? Oh, BCI2, but for Wakan. So I'm going to subset from this. So that I'm going to use the subset function because I want only Wakan, right? And I want uncia location to be equal to Wakan. Okay, and that should subset only the BCI for Wakan. I will do the same for Altai. Just replace this with Altai. Okay, and that should give me the BCI for Altai. I can check the length also. I won't write it in the script because I'll just write directly in the console just to do a quick check. The length of BCI Wakan 62, and the same for Altai. So I know I have 61 values for Wakan and 41 for Altai, which does seem to fit if I look at the summary of Uncia. I do have 41 letters from Altai and 62 from Wakan. So it matches, so it's good. Okay, now let's do a box plot for BCI Wakan. And this is what I get. This is the box plot. So if you're not familiar with the box plot, this is the values that you'll get is this. You'll get the median. That's the black line that you get in the middle of the box. You will get the first quartile and the third quartile. And then you will get also, so that's the size, that's the width of the box. This is also something you can call the interquartile range. And the whiskers here on the side of the plot kind of tell, it just gives you an idea of like, if there are points beyond these two lines, then these could be considered outliers, potentially. They kind of seem to deviate a little bit from the rest of the data. And we had already seen these from previous plot when I plotted that distribution, and we saw that there was a couple of outliers. Of course, the big leopard, I'm guessing might be that one. And this is another one. Oh, sure, wait. I'm realizing now we're looking at BCI. So actually, these outliers might not be the same leopards, but we do have two outliers. So yeah, if we're looking at length, then we would have the one we talked about. But I don't know if this outlier here, this is the max BCI. I can look actually at which leopard it is. So I could look potentially at, okay, no, sorry, forget that. I will skip that. I'll just build another box plot for Altai. Not spend too much time on this. And Altai, you can see, okay, there's no outliers clearly, because there's nothing going above or beyond these whiskers. We can't really tell, okay, does that mean it's bigger or is it a lesser BCI than Wakan? This is where it would help to have the box plots next to each other. So that's what I'm gonna do. So for single values, yeah, you can just put that vector here in the brackets of box plot as the argument. But I could, yeah, use that formula function, like that formula form to get that. So what I want is BCI2. So I'm going to use the actual Uncia dataset for this. So BCI2 will be on the y-axis, right? This is why it's going to go here. And the formula will, I just use this tilde here. And I want it to be by location. This is going to be the x-axis. This is what you want your box plot to be plotted like. So on the left side of the tilde is going to be the y-axis, the BCI. On the right-hand side is going to be location. Of course, here I'm only putting the names of the columns. The box plot needs to know where these names come from, which is why you also need. If I do this, it will not understand. It will return an error. So like object, he thinks that's an object, which of course is not going to work. So I need to specify what data I'm taking that from. The data is a data argument, is going to be Uncia, and then he will find that. He will look in the data set, look for columns called location and BCI2, and plot accordingly. This is what I get. Okay, now I get box plots that make a bit more sense and which I can use. And this is what we can see. We can see that Wakan seems to have leopards in slightly better body condition than Altai. the question is, okay, we see a difference, but they're not that far from each other. So is that a significant difference or not? And this is what the hypothesis testing will tell us. Okay, so I guess Anne, you can help me with the steps.
Okay.
So the first we want to plot, right, the two to make sure they're normally distributed.
One second. Which one? Error now. Did we say two not found? If that should work.
Okay, so I'm just gonna go ahead. So the first thing we want to do, remember the t-test has, which will apply here.
Okay, refer to it with the data $ and see.
Can you do that in the chat if I can continue? Or do you want to address some questions here now?
Oh, no, I'm just addressing your question. It worked fine. No, you had an error. I thought that's what.
Oh, no, I was just demonstrating that if I just put BCI2 in location without specifying the data, I get an error.
Okay.
No, I want you to help me with the steps for the hypothesis testing, not the error.
Oh, the steps was, sorry, I was answering a question here. So first, check for normality. We can just make a density function.
T-test, which will apply here. We think it might be suitable because we have quite a few observations, of course. But yeah, so one assumption is that the data should be kind of normally distributed. So let's check if BCI is kind of normally distributed. So for this, I'm just gonna plot it. I could do a test. Again, I told you there are some tests you can apply to check normality, but I usually prefer to simply check it visually with a histogram. Actually, so it's not plot, but the histogram that I want to use. And I'll just plot Wakan, BCI Wakan. Actually, I'm going to plot Unsia BCI Wakan. This is what I get. Wow, it's actually really nicely normally distributed. Yeah. And I'm going to do the same for Altai. Okay, Altai is a bit more spread out.
But it's still vaguely normal. Like this is something we can work with for t-test, but what is important is the variation.
Right. The variation we can check with, we can either calculate the standard deviation or we can look at the box plots. Just gonna check the histogram for BCI2 overall, like with the two locations pulled together. And okay, again, we get something that kind of looks like a normal distribution, a little bit of it's a little bit left skewed, left skewed, but not so much. Yeah. All right, okay, so if I look at the box plot again, I can actually see the variation, how much there's a bit less variation in Wakan, as you can see. I forgot. Wakan had more leopards though, so.
Yeah, so which is why variation is less, right? Higher sample size.
Yeah, no, but Wakan has, sorry, you're right. Less variation because we have a higher sample size. We can also look at check homogeneity of variance. So I can just look at var of BCI Wakan, and that's not right. No, is that right? Okay, I'll just look at the standard deviation. And Altai. Okay, and we can see the values are not too far from each other. So, and there was another assumption, right?
Yes, homogeneity of variation, yeah.
So we have normality, assumption of normality, the variance.
Yeah. And as you can see, the variance is slightly different, but it is comparable. Like this much variation in the variation is should be fine.
Oh yeah, sorry, and of course the data points should be independent. We should not have, let's say, for example, like two observations from the same leopard, because then it would not be independent. But yeah, we are assuming here, yeah, all the observations are independent. They're from different leopards, and one data point is not going to influence another. That's another assumption. Okay, so let's just go ahead and apply. Okay, so we want, so step one, state hypothesis. So state the null hypothesis. And it will be that the mean BCI at vacant is the same as mean BCI at alta. That's the null hypothesis. We assume that there is no significant difference between the two. Let's go ahead and do step two, which is the alternate hypothesis. It would be, so this is not code, this is just text, which is why I'm putting these hashtags here so that it doesn't run. The mean BCI are different between locations. Okay, so that's the alternate hypothesis. If we don't have, like, there's no reason for us at this point to think, okay, vacant is definitely should be bigger or should be lower. Can someone tell me what kind of t-test we're gonna do? Remember that there's pair t-test, there's one sample, two sample. So if you can write in the chat what you think we should be using here. Two sample t-test. Yes, so we have two samples, but they're not paired. They're not, it's not like we had a bunch of leopards and then we're looking maybe at the same leopards either later in time or after a particular treatment. Or it's not like we took leopards from vacant and translocated them to altai. That could be a setting, actually. It could be you have leopards that you want to reintroduce somewhere. So you take individuals from one location, put them in altai, let's say, and you want to look at the BCI. Is the process of reintroduction having an effect on their body condition, maybe because of stress? In this case, because that would be a paired t-test because you're looking at the same individuals before and after, and the two samples, of course, will be of the same size because you want to it's the same individuals, right? So it will be, yeah, the sample one will be the same size as sample two, right? But here we have more leopards in vacant, we said. So step three, I need to remember myself what step myself. Okay, set the confidence level. By default, we'll put an alpha level of 0.05, like it's kind of like the standard alpha level. We put alpha. So this is our, remember, this is our confidence level, like our significant level of significance. 0.05, which means that if we find a significant difference between the two, we will be able to say that we are 95% sure that that there is a significant difference between the two populations. If we set the level at 0.01, then the likelihood will be 99%. So if you could find a significant difference at that level, you're even more confident that there is a significant difference. But yeah, we'll use the kind of default value here of 0.05 just because. And the step, there's a fourth step, right? The fourth step is compare the test statistic, right? So we're not going to use this table. Like, remember that in the past people use these tables. We're going to let R do the job. Oops, step 4. The t-test. So let's do it. Okay, so how does it work? Let's look at the help file for a second. For t-test. Okay. The t-test. Okay, the t-test, of course, minimum it needs one vector, of course. We want two vectors, of course. This is it's a pair t-test, so we want an x and a y. So let's go ahead and do that. We'll move the question mark. So x will be BCI vacant. Y will be BCI altai. I don't need to put x equal and y equal, actually. I don't necessarily have to do that. R would expect that the first argument I put is X and the second would be Y. So if you are respecting that order, you don't need to put the names exactly. But just to be on the safe side, we can say, okay, X is going to be that, Y is going to be that. Then we know that there will be no miscommunication between U and R, and we all know what we're talking about. The alternative here is also an argument you can put. It means either you can choose two-sided, that's the default. So by default, it will be a two-sided test, meaning you don't know in which direction it's going to go. You don't know if YK or Altai will be in worse body condition. So we're going to use the default here, which means, of course, I could leave it empty because that's the default. But just for the sake of writing that function, I will actually specify it. So it will be two-sided. Paired is going to be false. So I'm not going to put anything here because it's not a paired t-test. And the, oops, and right. I don't actually need to put the alpha here because what this test is going to return is the actual p-value. The p-value is what you're going to use. So if the p-value is less than 0.05, then that means there's a significant difference. If it is more than that, then there is no difference. And that is how you do it. I don't need to specify the alpha level there. It's just that when I look at the p-value, that's when I apply it. Either less or more than 0.05. Okay, so let's try it and see what we get. Oh, sorry, I need to, there's something else I need to say. Var equal. So remember that there is, the variance should be equal to be able to apply a t-test. There is so there is, if the variance is not equal, if you're not sure if they're going to be equal, there is a variant on the t-test called the Welch test, and R automatically apply it. It automatically assumes that the variance may not be equal, and it applies the Welch test by default. I want to just, for the sake of this exercise, I want to apply the actual t-test. So we'll change this R equal. So by default, it is
false,
but I will set it to true. So I will tell R the variance between the samples is zero. You'll see that it will, if I do that, it will not say Welch test anymore. It will say t-test. Then it's but if you compare the two, you'll see that there is not much. The result will be similar. Okay, so this is what we get. We have the t value. This is a t statistic. If you remember the t slide here. Oops. Test. Oh, I don't have the. I had the. There was formulas that I don't have, unfortunately, to calculate the t statistics. There is, of course,
correct,
manually, but R does that for you. So the value is 4.7027. Degrees of freedom is 101 because we have, that's n minus 2, I guess. Yeah, 2 because there's 2 groups. And it tells you the p-value. The p-value is tiny, as you can see. It's way below 0.05. So the alternative hypothesis was that there's a true difference in means, not equal to 0. It tells us the mean of x. The mean of x for, so that's Wakan is 0.73. The mean of y is 0.7. So we can say with very high confidence that the two locations have a different BCI, Altai having a lesser BCI than Wakan. So somehow the body condition of flappers and Altai is a bit less than the ones in Wakan. And this is getting, and there you can get into interesting questions. You can ask yourself, why is that? Maybe it's to do with like, maybe these lepers are just different. Maybe they're subpopulations and they're just morphologically a bit different. The ones in Altai maybe being slender. Could be something to do with the habitat conditions, maybe though there's less prey in Altai. So just to give you an idea of like the kind of questions we can answer with this kind of data and this kind of test. So t-test is a very simple statistical test. It can be implemented very easily. And that, I guess that's, we're going to be, oh yeah, we have one more slide, right?
Yeah.
That's it for this.
Yeah. Okay. So basically, the last slide is just to let you know that, what do you call it? Yeah. In case your data is not normally or approximately normally distributed, which can be in a lot of different situations, what you can do is apply something called non-parametric tests. And so there will be an equivalent of a non-parametric test for literally every parametric test you can think of. Parametric tests are basically just the kind of tests we discussed right now. They use things like statistics like the mean and standard deviation to compare populations and infer whether they're equal or different. And another drawback of parametric tests is that it has to be numeric variables, because obviously you can't calculate mean or standard deviation without numbers. The non-parametric tests, on the other hand, they use the median more often than the others, and sometimes they use ranks and like the order in which things appear, compare populations. And in non-parametric test, you can also use categorical data. So if you have any kind of categorical variables that you want to compare, what you would be using is non-parametric test. And there are various drawbacks to each one of them. For parametric tests can be influenced by outliers, but because non-parametric uses median, it's not influenced by outliers. But it does have lower statistical power. Like you might have to do a couple of tests or like add some data analysis to like sort of gain more confidence in your non-parametric tests. Like if you do only non-parametric tests, there might be reviewers who will not be particularly happy with the results that you get. But so just so you know that there is this option for data sets that cannot be tested using parametric tests. So yeah, that's it for today. Any doubts? Any specific section?
Actually, I wanted to ask one thing, which is not being covered today. If I may do that now, or maybe I can send you an email.
I mean, okay, if
yeah, no, I can. Yeah. So the thing is that I have a very similar data. Fortunately, I was very excited when I saw the length and weight data that we were doing, because I have a very similar data for my project. In that, I have to actually find out length and weight relationship. It is on sharks. So I've kind of found the length and the weight of sharks. And then I've tried to find the length and weight relation with respect to the sex. So there are different male and female equations that I've got of regression. But I was trying to figure out how significantly different both equations are, or are they just same? So I had to undertake ANCOVA for that, considering covariate as length and independent variable as sex, and one dependent variable, which is weight. So I tried to do the ANCOVA, and I realized that a lot of assumptions are not being captured. Or like, for example, normality of my dependent variable weight. That I was taking log of weight, ln weight and ln length. So ln weight is not really normal, and the residuals are also not following the normal distribution. So I was like, okay, let me go for the non-parametric ANCOVA. Then I found out somewhere there's something called robust ANCOVA, which can be taken up as a non-parametric ANCOVA, but I'm not able to get any literature which can explain the results of robust ANCOVA. Because there's different points that I'm getting, and the 6-7 points wherein it's comparing the ln w and ln length and giving me a p-value. So it's not like how general ANCOVA gives the results in R. Like we get an F value, we get a p-value, and we can figure out that whether it is significant or not. But yeah.
So Haripya, yeah, that sounds interesting. We will actually do more regression like later. Like we will do something that is not just a t-test to compare data. You might have answers to your questions there. So I would wait a little bit just for the next couple of sessions to maybe see if you get more answers. Otherwise, feel free to drop an email. We'll be more than happy to help you.
Troubleshoot that.
Yeah. Okay. Thank you so much. I might just drop an email so that if you could share any literature, like I can just go through it.
Yeah, send us an email, no problem. You can even put it on the group. Maybe other people will have ideas.
Yes. That'd be fine. Okay. Thank you.
Anyone else has questions? maybe in the chat.
No, there isn't. Okay, so I hope that means you guys understood everything perfectly. But yeah, if you have questions later, you feel free to shoot an email and we can address them there. All right, thank you. We will see you next week.
Thank you, and thank